Hey there, Mr. Sutton back with another lesson on transformations. In this one, we will be performing dilations or stretches on functions. Let's start with a working definition of dilations. A dilation is a stretch or a shrink of a graph. Mathematically, we're multiplying by a number. Now, you might think, well, we were multiplying by numbers when we did reflections. True, with dilations, we're multiplying x or y by a number that is not just 1 or -1. So this is going to affect the size of the graph one way or another. To see exactly what the relationship is here, go to this website. This is a GeoGebra website. Pause the video and take a sec to play around with the A and B sliders on the sine function on that website. And then go ahead and answer the following questions. So as you increase the outside multiplier, what happens to the graph? And in what direction? As you increase the inside multiplier, what happens to the graph and in what direction? And your options are stretch, shrink, vertical, horizontal. Here's the actual website if you go there. We'll play around while I'm waiting for you guys to play around with this. So here's the A value. This is the outside multiplier here. Look what happens to the graph as I increase that. Look what happens as I decrease that. Increase, decrease. So taking a look at that, it looks like as we increase that multiplier outside, the graph is stretching, and it is doing so in the vertical direction. All right, let's go back there and see what happens when we mess with the inside multiplier. So this B value is getting multiplied by all your inputs, and we won't worry about this H and this K. That comes a little bit later. So B values, as I increase that, it looks like the graph is getting more shrunken in the horizontal direction. As I decrease the inside multiplier, well, now we're stretching out horizontally. So that's a little counterintuitive, but the graph is definitely shrinking as you increase that multiplier, and it is doing so in the horizontal direction. So in general, we can make some generalizations here. If you have outside changes, those are going to affect the up-down, the vertical of the graph, and they're going to do exactly what you expect them to do. Increasing the outside multiplier stretches us in the vertical direction. Inside changes, on the other hand, affect the horizontal, and they actually have the opposite effect of what you expected. Increasing the inside multiplier shrunk the graph. Instead of multiplying by that multiplier, it's almost like you were dividing by it, or multiplying by the reciprocal. Now, a lot of people have trouble wrapping their minds around this idea of horizontal changes being opposite of what you expect. So I'll make an attempt to explain kind of the intuition behind this. So why are horizontal stretches the opposite of what they look like? Let's say that we have a function, f of x. Let's say x is the time since a test started, and y, or f of x, is the number of questions answered. So you're taking this test, and as time goes on, you're answering more and more questions. Let's say it's a 2-hour test. So as you get closer to that 2-hour mark, you kind of increase your rate of question answering until you are done. This is the y value, done. Now let's say that your watch is broken, and unknown to you is moving twice as fast as it should. So let's say that instead of f of x, you have f of 2x. The inputs, the time that you're looking at as you're doing these questions, is twice as much. It looks like it's twice as much to you as it actually is. So how is the curve going to change based on that? If you plan to finish by 2 hours, what's the new finish time? Well, if your watch is going twice as fast, then at 1 hour, your watch is looking like you've already done 2 hours worth of testing. And you're like, aw, snap, I better finish a lot faster or else I'm never going to get this test done. So in response to what you think is your finishing time here, you get done actually a little bit earlier than you normally would have. And that is causing, if you notice, this curve to get shrunken toward the middle here. So when you're increasing your input, you're making your output happen sooner, just like trying to finish a test sooner if you've got a fast watch. You could think of it as the function trying to compensate for what you did to the input. So with all of that in mind, let's apply a few dilations to some graphs here. So we're going to use our piecewise function that we were using for the reflections. Our function here is y equals 2 f of x. This is your original f of x, and we're multiplying the outside of the function by 2. Now, outer changes, remember, are vertical, and they're exactly what they look like. So you're multiplying the y values by 2. You're stretching this. So let's take all our y values, all our corner points here. This point, the y value is 0, so that's not going to go anywhere. This value is now going to get multiplied by 2. This value, same thing. This value down here is now negative 2 instead of negative 1. Same thing down here. And then, let's see, this one stays where it is. This point is going to be twice as high. And connect the dots. So there we are. This graph has been stretched vertically as a result of this transformation. Here's another one. Pause the video and try this one on your own, and note that we have a negative 1/2 out in front. All right, let's see what you did. So because this is an outside change, it's going to affect the y values, and we're going to do exactly what it looks like we're doing. So we're multiplying all of the y values by negative 1/2. Now, in terms of what's happening, because of that negative, we are reflecting vertically, and because this is a number that is, when you multiply something by half, it makes it smaller, this is going to be a shrink vertically. So this y value stays where it is. Positive 1 now becomes negative 1/2. That's 1 times negative 1/2. 1 becomes negative 1/2. Negative 1 is now going to become positive 1/2. Same thing to this point here. And this positive 1 is going to become negative 1/2. So we did two things on this. We flipped it, and we also shrunk it vertically. We're going to do one more of these graphing problems. If you feel comfortable with our conversation about inside changes that we had earlier, feel free to pause the video and try this one on your own in pencil first. All right, so let's see what we've got here. This 2 inside, since this is an inside change, remember it's going to have the opposite effect of what you expect. So instead of multiplying x by 2, we're actually going to multiply x by 1/2. This is going to be a horizontal shrink, multiplying x by half. So let's go through and do that to each of our vertices here. So this 3 becomes a 1.5, negative 1.5. Negative 2 becomes negative 1. The negative 1 that we already had there is now a negative 1/2. 0 is going to stay where it is because you're multiplying by 0. 1 becomes 1/2. And then we have this point over here, 3 becomes 1.5. Connect the dots. And there is our horizontal shrink. To give you a little bit more practice with dilations, we're going to work with an individual point now. Let's say a graph has a local maximum at negative 8, 20. We want to know where that maximum is going to move as a result of these 4 transformations down here. We'll do the first one together, and then you can try the last 3. So for this first one, we have f of negative 2x. Since that's inside, that's going to affect the x values, and it's going to be opposite of what we expect. So we're multiplying all the x values by negative 1/2. So x comma y is going to become negative 1/2 x comma y. So up here, negative 8 gets multiplied by negative 1/2. That becomes positive 4, and then the y value stays exactly the same. So positive 4, 20. No jokes, please. All right. Pause the video and try the next 3 on your own. All right, let's see what you came up with. For this one, this is outside, so we're multiplying the y values by negative 2. So x is still negative 8. 20 becomes negative 40. Here we're multiplying the y values by 1/2, and it's exactly what it looks like. So we've got x comma 1/2 y. So negative 8, 10. And here we've got inside multiplying by 1/2. Again, it's opposite of what you expect, so the x values are going to get multiplied by the reciprocal of this, which is 2. So we're going to have 2 times -8, which is -16, comma 20. That's it for dilations, for now. It was actually no accident that we looked at the sine function in our warm-up, because you're going to be using these things on sine and cosine later on this year. But until then, this is Mr. Sutton, signing off.